Hey, Rui, come on in. Come on down. Let me go here. Come on, questions. Okay, cool. All right. Everybody, come on in. Got the breakout rooms ready. Okay. Let me start sharing these. Yeah, and that's it. Someone came in, but I can't tell who it is. Oh. Whoa. There's 3 grants.
Sorry, that was my bad.
You got your computer, your phone, and your tablet?
Not quite. Avery doesn't have the link, so I was trying to pull it up on my phone so I could text it to him easily, but I think I might just have to do it manually.
Okay, which link is this?
The link to get into this meeting.
Oh, okay. Just tell him to go to Canvas and then click this right here.
Yeah, I think he knows that. I was assuming that maybe he was... I don't know why he would need it from me, but...
All right, well, we can wait. What exactly are you guys clicking?
Exactly what you said, that link right there.
This right here? Okay.
I think he might be stuck on mobile, though, or something like that.
Okay. Oh, yeah. Let's wait for everybody else. Hopefully they show up today. Check this morning, nobody dropped.
That's good.
Yeah, let's see here. I think I'm gonna, yeah, I'll leave it like this. Whoa. Bring my mouse on this side. There he is. Oh, I feel weird. So just on the chat, if you can just put what kind of device you're using to log in, just so I know, please. Computer, all right, cool. Mitchell, what can you put on the chat what you're using, just so I know?
I'm using a computer.
Computer, okay.
I need to get a keyboard because I can't type right now.
Oh no, okay. All right, make sure, hopefully if you haven't downloaded the PDF for today, on 13.6, Isomorphic Groups. All right, guys, so welcome back. We have what, just a few weeks left. Quick announcements. I did post that on May 7th, there's this thing going around where different mathematicians are being asked if they can kind of do a little Q&A. So one of the events that's happening is this Thursday. So if you're planning to become a mathematician and you kind of want to know more about what that entails and what does their work look like besides teaching, here's a good time to do that. So that's cool. I wish I had that opportunity when I was an undergraduate. So you can check out that announcement with more details there. And then let's see, in terms of homework, you have one homework assignment due this week. And then you have, we're gonna finish off, oh, homework 24. Whoops. Okay, I'll fix that one. That shouldn't be, I'm gonna have to update that one, okay? So I believe, blah, 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 I'll look it up. But that should be on the next chapter, which I think is chapter 14 or 15. I'm getting confused between the textbooks that I was using this time and last time. There is no quiz this week. And again, here's the counseling information if you need anything, personal counseling or academic counseling. All right, guys, so I think it's chapter 12, okay. Here, I guess I can just say it here real fast. It will be, that's right, chapter 12. But I just have to see if it's one section or two sections. I'll update that later. All right, guys, so let me go to my iPad. So we're going to, oh, wait, what is this? Oh, there we go. Okay. So we ended up talking about permutation groups and dihedral groups, the dihedral group. So remember that the permutation group, this notation here, permutation group S3, means it's all the permutations that that are bijections or arrangements of elements of the set 1, 2, 3. Okay, so it contained 3 factorial elements, so that's 6 elements. So here are the 6 permutations. The dihedral group, that was a little different, and what that was is the dihedral group D3 looked at a 3-sided regular polygon, which in this case is a triangle. We looked at different symmetries on it, so there was a way that you can reflect it across this axis, and you can reflect it across this axis, and then there was a symmetry of rotation, okay? That's where we left off. We looked at these groups because they had their own, there was a set and there was a way that you can combine the elements in the set in certain ways. And what we ended up with was I had you guys explore more with the dihedral group. And I want you guys to, you looked at examples of different kinds of reflections. And at the end, we realized that all the symmetries had a one-to-one correspondence with permutations. So for example, the symmetry where you reflect across the axis A0 switches the 2 and 3 on this side. And it left 1 fixed. So then the permutation that we realized that corresponded to was a permutation that swaps 2 with 3, but leaves 1 fixed. Okay? Then we looked at the reflection A1. That one swaps these 2 corners, but leaves this second corner fixed. So that corresponded to the permutation that swaps the elements the corners 1 and 3. So 1 goes to 3 and 3 goes to 1, but leaves 2 fixed. And the second or the third reflection, which reflected across this axis, leaves 3 fixed, and it swaps the other 2. So how do you guys feel about how we were doing what we did last class and the connection that we found between these two, the elements of these 2 groups? Good? Okay. All right, sweet. So then rotation, just remember, if we rotated once, 2 goes to 3, 3 goes to 1, and 1 goes to 2. So that corresponded to 1 rotation where, let's see here. I did these wrong, crap. I rotated it the other way. I'm saying 1 goes to 3 here. It's supposed to be counterclockwise. No worries. We'll just have to edit it. Let's see here. All right, help me out. And then I'll just update the new PDF and post it on Canvas. So this rotation where I rotate only once, where does what one get sent to which element? If I just rotate it once.
Two.
It gets sent to 2, right? Because 1 gets sent to 2. And then 2 gets sent to 3. So 2 gets sent to 3. And then 3 gets sent to 1. Okay? And then let's see here. So then if we do 2 rotations, 1 gets rotated 1, 2 over here. So 1 gets sent to 3. And 2 gets rotated twice. So 2 gets sent to 1. And then 3 will get sent to 2. Okay? So I made a little boo-boo on that. Sorry about that. So those are the correspondence that we found between these elements. So what I want you guys to notice is what we're going to talk about today is how we're going to look at 2 different groups and how there's certain functions that connect those 2 groups. But there's certain properties that they have to hold, okay? And then we'll do some proving to kind of see how we would make those arguments. So I want you guys to notice that this describes a bijection because each element in the dihedral group corresponds to exactly 1 element in the permutation group. Okay. But what I want to see is S3, notice that S3, the permutations, combines elements using the binary operation of function composition, while the symmetries in the dihedral group combines the symmetries using the binary operation little star here that we discussed last class, where if you combine 2 different symmetries, so if I was to do symmetry S0 with R2, I first perform symmetry R2 to the triangle, and then whatever I get left, then I perform symmetry S0. Okay? So it's just kind of like an order here of the type of symmetry that you're going to perform. Ooh, I'm curious. I changed these. Now that I realized I made a mistake, I wonder if what we're going to say later is actually a little different. But let's see what happens. So even though there's a bijection, what I want us to explore is, will this bijection described above preserve the binary operations? And what I mean by that is if I multiply 2 elements in the dihedral group, I'm going to produce a new symmetry, and then F is going to send that resulting symmetry to a permutation. Would that be the same if instead I sent each of these original symmetries to their corresponding permutations and then combined the permutations, the 2 permutations together, where the left side and the right side produce the same result? Okay? So let's take a look. So let's see. We're gonna get symmetry S0 and R1. And then just to review here, I'm saying it's R2, but let's take a look. So I'm gonna go scroll up to the picture we had, S0 and R1. So let's do S0. Let's see, S0 and then R1. So we're gonna start out with the triangle here. Let's see, we're gonna do it 3 times or twice. So I start with 1, 2, 3. When we perform R1 to the triangle, that means I'm going to rotate it 1 time. So 1 gets moved over here, 2 gets moved over here, and then 3 gets moved over here. And then we're going to perform this symmetry, which is the reflection across this axis. So I'm going to now reflect across this axis right here. and we're going to get 1 moves here, 2 moves here, and then 3 stays put. Okay. So now the question is, what symmetry would this equal if we performed this symmetry to the original triangle from the beginning? So if my original triangle has 1, 2, and 3 here, what symmetry needs to be performed so that the 3 ends up here, the 2 stays fixed, and the 1 ends up here? What symmetry is that? Oh, it is different. Okay, I knew it was going to be different. All right. What do you guys think? So from here to here, we performed R1. And then from here to here, we performed S0. Does this procedure look correct to you guys? Am I making any mistakes? Let's see, you guys are saying
fine.
S1. Yeah. Yeah, so you guys are saying S1. That means that we just reflected these two first. Okay. So that would be S1. Okay. And let's see. See, I knew changing things here was I was thinking of this differently when I was writing my notes. So let's double check. Ah, I got it wrong. Okay, I wrote R2. Okay, sorry about that. So this should be corresponding to S1. Okay. So when you combine the two symmetries, we get S1. And then we plug that into our function f. And f needs to send it to a permutation. So we go up here and we say, okay, S1 is being sent to the permutation 3, 2, 1. So that's being sent to 3, 2, 1. Okay, so that's what happens on the left-hand side with this example, this concrete example, okay? We end up with the permutation 3, 2, 1. Now let's see what happens if we do this on the right-hand side. And I might change a couple of things because I did my original permutations incorrectly. So let's see, S0 gets mapped to 1, 3, 2. Let's double check that. If I plug in S0, that corresponds to 1, 3, 2. That is correct. If we plug in R1, it's going to be sent to 3, 1, 2. Let's double check that. Ah, wrong. R1 corresponds to 2, 3, 1. So let's see. That's a mistake. 2, 3, 1. 2, 3, 1. Okay, so now that we corrected that, so now instead of multiplying the symmetries first, we're going to first plug in those symmetries into my function here, figure out what permutations they correspond to. So this is supposed to correspond to 2, 3, 1, and this one's 1, 3, 2. So now I got each of these, I sent them to their corresponding permutations, and now I'm going to now use the binary operation of function composition to double check. Let me erase this because it might be wrong. To see which function, which bijection this corresponds to, okay? So remember, we're doing function composition. So that means that you're plugging into this function first and then this function. So let's see, let me use a different color here. Let me move this a little down so I have more space. And let me make it a little smaller here. Now, this might not be true. So let's double check. So let's see, 1, 2, 3. So if we plug in 1 into this function, it's sending 1 to 2. It's sending 2 to 3. And 3 to 1. But then when you plug in 2 into this function, 2 is being sent to 3. 2 is being sent to 3. 3 is being sent to 2. 3 is being sent to 2, and 1 is staying put. So 1 is staying at 1. So then that means that overall, when you plug in 1 into this composition, it's being sent to 3. So 1's being sent to 3 here. 2 is staying at 2. So 2 is staying at 2. And 3 is being sent to 1. So that corresponds to that permutation. So now back to my original question. Oh, fuck, they are equal. Okay. So my notes are incorrect then. So that means that in this case, we do, for this particular scenario, we do end up with the scenario that the left-hand side, if you combine the symmetries first and then apply the function, they gave us this permutation, versus if you apply the function to each symmetry first and then combine it using function composition. In this case, we did end up getting the same elements, the same permutation.
Can I ask about this real quick? So
Go for it.
you're applying the second one first, right? Because that was the way it was presented, as you apply y to the triangle and then x.
Yes.
Okay.
Yeah, because that's the way we defined it in the notes last class.
Okay. So then.
Let me double check. Hold on. Let me double check. Right.
Yeah.
Let's see. Let's double check.
That seems right to me. It was about the next part that was confusing.
Okay. So it says, consider this binary operation such that x times y is the symmetry to the triangle by first applying y. Yeah.
Okay.
Ooh.
So then, if you apply x, then shouldn't the first thing stay the same? But you've got 2 going to 3.
2 going to 3. Oh, you're talking about function composition here?
I'm talking about the second transition you made.
Are you talking about this step or this step? 1, 2, or 3?
Sorry, your cursor's moving really quickly on my screen.
Are you talking?
I'm talking about what you have written in blue down here. This last.
Oh, this one here.
Yes, exactly.
Okay. Did I make a boo-boo? Let me see. So 1 got sent to 2. 2 got sent to 3. 3 got sent to 1.
Yeah, that first step makes sense because it's just copying that first symmetry.
That's right.
And then the second one, the first value should stay the first value. So I think 2 should stay 2, shouldn't it?
Well, okay, so this function here, let's see. This guy here is really a bijection, right?
Yes.
Let's call it G. Let's call it the bijection G. So that tells you that when you plug in 1 into G, you get 1. When you plug in 2 into G, you get 3. And when you plug in 3 into G, you get 2.
Oh, so it's not dealing with the positions, it's dealing with them as individual numbers?
Yeah, as individual elements. That's right.
Huh, okay.
Because if we call this G and we call this one H, right?
Yeah.
What I was kind of doing here is you were applying this composition, let's say to 1. Let's say to 1, right? Ah, what the hell? Let's say you're applying it to 1, this case here. Then you're doing this. But H is sending 1 to 2. And then now 2 is being inputted into G, but G sends 2 to 3. Does that kind of make sense?
I think so. Doesn't that mean that no matter what input you have, the secondary function would override it though? Hold on, I'm just trying to.
Well, no. So then from the final result, this composition function sends 1 to 3.
Okay, I see.
Yeah, because like let's say you used a different permutation here, right?
Mm-hmm.
And 1 got sent to 3. Let's say that, right?
Yeah.
Then here 1 would get sent to 3, but then G sends 3 to 2.
Okay, I
So
see
then
it.
it would, yeah, it would look like this. So it does matter which one. It does matter the order in which the functions are sending their elements.
Okay, thank you.
Mm-hmm. Okay. All right. So let me. I guess I'll leave those. No, I don't want to leave those there. Okay. You guys can, yeah, write those specific steps. I just want to leave it here so that when I save it, I can reuse it. All right. So in this case, I was incorrect originally. We do get the same permutation on both sides. We get 3, 2, 1. 3, 2, 1. Ooh, fun. Okay, that makes the class a little more fun in this case. We'll see why later. So from just this example, right? Now the question is, so is that going to be true no matter which symmetries I start with? I will always end up with the same permutation on both sides. Okay. It doesn't matter if I multiply the symmetries first and then plug them into the function, or if I plug them into the function first and then I multiply them, or I compose them together. Okay. So what I'm saying here is incorrect. So it says, let's see, it says, therefore, sets S3 and D3 are alike, but as groups, oh, I know what I could do. I can say, but as groups, are they different? Are they, whoops, are they different? Sorry for the little mistake here I made. Are they different? I'll squish it. I'll fix this later. Are they different? Okay. Meaning, do they behave differently? Okay. Like for example, we already know that each of these are both groups, and each of these have their own inverses. The question is the inverse symmetry of S naught also the inverse permutation of this one, right? So that's what I mean by they behave. Are they different or not? The groups, like, do they actually align in every single way? We already know there's a one-to-one correspondence between their elements. If I multiply them, we saw an example where it seems like no matter which way you multiply them and then transfer them between one another, we're getting the same result. The other question is the identity going to be sent to the identity? In this case, we defined R naught to be the identity, which is the rotation where you don't rotate anything, and it's being mapped to the identity permutation. So that seems to be happening. So one thing we just don't know are the inverses. Is it true that the inverse of a symmetry is equal to the inverse of the permutation that it corresponds to? Okay. So those are the questions we're gonna figure out today.
I had a quick question.
Yes.
Dihedral groups only contains rotations and reflections, right?
Yes.
Okay.
Yeah, that's right. Let's see, in the, well, the homework is due after later on. Okay, never mind. But yes, that's correct, Max. Only rotations and reflections. Okay. So up here we saw an example where the function was a bijection, but it also seems to be preserving like the binary operation for each, depending on the group that we're dealing with. So that has a special name. And it says for groups G with binary operation being an asterisk symbol here, and another group H, here we're just going to use a dot to symbolize a different binary operation. If there exists a bijection phi from G to H such that phi is operation preserving, and that means exactly what we were just playing around with, that if I combine my two elements in G first and then plug them into my function, it would be the same thing as if I plug them into my function first, sending them to elements in H, and then combine them using the binary operation in H. So if this is true for all elements in G, we say that groups G and H are isomorphic. So not only is there a bijection between them, their binary operations also is kind of contained. Okay, it also follows through. And these types of functions are called isomorphisms. Funky name. I should have looked up where those words came from. And does anyone have any idea? Anybody good with what's that term? Etymology, I think it's called.
Isn't that bugs?
Oh yeah, you're right.
I also have a question about the phi notation.
Yes.
So is it saying that for phi of A star B, where B happens first and then A?
That doesn't necessarily. So it doesn't necessarily have to be B or A first. It just depends on how you define the binary operation.
Okay.
Yeah. So like, let me go back to when we were first doing groups. You see all these binary operations that we used for these things, or I guess these were non-examples of groups, but like if you were to add 3 plus 2, here 2 coming before 3 doesn't really make sense, right?
Right.
It's like you just add them. But in the dihedral group, we can't really add symmetries, so we define them in this new kind of method way of saying, do this one first and then this one second.
I see.
So yeah, keep going.
Does that mean that the left-handedness or the right-handedness or the direction of the operations is inherited by the group definition, not necessarily that there's some sort of universal, like you have to always go left-handed first, or
That's
you
right.
always have to go right?
Yeah,
okay.
That's right.
Got it. Cool.
Yeah. Now, one cool thing to notice though is that like we just saw right now, there are binary operations where it doesn't care about order, right? Like it just tells you somehow put them together, like addition or multiplication. The order doesn't matter. It doesn't matter which one's on the left or right. But notice that for the groups that we're dealing with, function composition does care about order, because depending on how you compose two functions, you get different results. And the way we defined the binary operation for the dihedral group, also it does care about order. So that's another hint that maybe both of those binary operations behave differently, but they're probably behaving the same with the elements that they're dealing with. Okay. So that usually tells you, oh, okay, the way you would use the vocabulary here is maybe the symmetric group and then the dihedral group are isomorphic, meaning that there exists a bijection that is operation preserving, meaning this notation. Okay. So let me say some quick remarks. So isomorphic groups look different, but are really the same group, meaning that the elements look different, but they're behaving the same way, no, depending on the binary operation that they are defined on. Okay, so they might look different, but they're actually behaving exactly the same. And one is a disguise of the other, since the elements behave the exact same way, like what I just said. Okay. So it's kind of like the analogy I would give you guys for this is your understanding of numbers, right? Where let's see, where think of fractions, something like this. These look different, but when you're actually using and combining them with different numbers, they behave the same way. They follow the same properties that one would, and then the other also has to hold. Does that kind of make sense? Like they look different, but they behave exactly the same according to the binary operation we're using them with. Or here's another example, but I guess maybe you guys haven't messed around with complex numbers, maybe. So these look different, but because we're defining them to be equal, they'll behave and they'll follow the same properties when you use them with other values. Oh, here's another example. If we had, I'm giving you analogies, okay? I'm not giving you isomorphisms. I'm giving you analogies. If you have a function that looks like this, 2x plus 1, and you have this function that looks like this, 8x plus 4, they look different, but as functions, in terms of their graphs here, if you were to graph these two, oh, would they be different?
Yeah, that would be a little different.
Yeah. They would be totally different. Oh, I was thinking solutions of an equation. Never mind. I was thinking something else. Just kidding. Okay, that was a bad analogy. But that's what's kind of happening here. Okay, they're disguised as different things, but in terms of how they behave mathematically with one another, they're going to behave the same with one another. And then notation here. So if you have two different groups and they're isomorphic, the way you write this in math is you just say G is, and then you use kind of like a similar equality symbol with H. So this would be read as G is isomorphic to H. Okay. Let's see here. I want to see how you guys are doing. All right. How's it going? Anything you would like us to revisit? Okay, it's not too bad. All right. So what I'm gonna have you guys do is I want you guys to play around with these things. I'm gonna give you guys three totally different groups. And so we're gonna play around with these two little groups given by these tables, okay? Here, the binary operation, the only way we know how they're related to one another is through the table, okay? That's the only rule you're gonna know here. We don't know if they're like adding or anything like that. It's just the table is what will define how the elements are related to one another, how they are combined. So with your group, I'm giving you two groups. G here has elements A, B, C, and H has elements X, Y, Z. I want you guys to recall that each element in a group must occur exactly once in every row and in every column. So some of you guys were saying, I'm gonna think of like Sudoku here. So I want you guys to try to work with your peers here on these problems. You might have to, if I can have someone in the group just share their screen and then maybe zoom in to the tables here so you guys can fill them out. Let me start making breakout groups. Let's see, there are, how many of you guys? Okay, so let's do, okay. Oh, it's having me. Let me see, can I just, oh, that's so annoying. Okay. Okay, let's recreate all rooms. We'll do 1, 2, 3. All right, let's try it out. Make sure you join, please. Let me have at least one of you guys volunteer to share your screen with the PDF. Oh, it's not open yet. There we go. Okay. All right, let's go check these guys out. Awesome, thank you.
X. C. A, B, C. For
Roy, do you want to do the other table? You think?
I don't know, but I cannot
Oh, you
turn.
can't do it?
Yeah.
Okay, that's fine. I'm pretty sure they're pretty much the same anyways.
Yes. C.
Yours doesn't work because it says A is the identity. So A star B has to equal B.
Ah, yeah, it does. You're right. ABC.
Star A, would that be B?
Right, because
I'll fill
A,
in this. You go with that.
since A is the identity, no matter if you do it on the left-hand side or the right-hand side, it will be the not identity thing.
That's a good point. Okay.
Yes.
Because isn't it, doesn't the function have to take in like another like elements of the group, right?
Yeah. So A goes to X, B goes to Y, C goes to Z.
Oh, okay.
By default, because each is paired with one unique
Okay. So how do we? Let's see. How do we represent that? Like as a what's the word for it?
You just write phi of A goes to X, like phi of G to H defined by phi of A goes to X, phi of B goes to Y, phi of C goes to
Right.
Yeah.
Let phi be the function that takes from G and goes to H.
Hold on. I forgot doing this is kind of annoying. I gotta make that. I gotta make this. This could be better, but I'm not too worried. What if we just did... Is that isomorphic?
Let's see.
So what are the conditions for an isomorphism? What must be true about that function?
A star B has to be equal to, sorry, function of A star B has to be equal to function of A dot function of B.
That's part of it.
Oh,
Maybe scroll up to the definition real fast.
dang it, I'm still in.
So you need it to be that as well.
Operation preserving.
And bijective.
And bijective, yeah.
Ah. Okay.
Which I think you guys already did by default. That it's bijective. Which is fine. I mean, in this case, it's easy because it's just 3 elements, right? You just assign
Right.
one to a unique one, and that's fine.
I mean, just making a one-to-one transition seems like it should, because they're essentially... Could you even say that star and dot are the same thing?
And that's pretty much what you could say with an isomorphism. That's right. That's exactly the idea.
So that's so by creating an isomorphism, you're proving that star and dot are, I guess, equivalent to each other?
Kind of, yeah. I mean, as functions, they're different because they have different domains.
Yeah, but
and codomains.
The actions they're performing upon their domains are essentially the same.
Exactly.
Okay.
How they behave with the elements are the same way that the other binary operation is behaving with its elements.
So, for example, if I had a function that went from R2 to R3, and we know R2 is a group on addition and R3 is a group on addition, I can say that the function that translates R2 to R3 is isomorphic because there is a bijection that takes from R2 to R3, and that no matter what R sub 1 plus R sub 2 phi R sub 1 plus R sub 2, that's still the same as phi R sub 1 plus phi R sub 2.
That's the idea behind it.
Okay.
Now, when you say R sub 1, you're talking about the previous examples, right?
Yeah.
That's right, yeah.
Okay. So in reality, this is a way for us to talk about or connect between different domains and codomains, even though on their face they don't really look similar.
Exactly, yeah.
Neat. Now
as math objects, they're different, but in terms of how they behave with one another, they're the same.
Oh, okay.
Yeah.
So I could connect like addition on the number line to addition of probabilities, or
Yeah.
multiplication of numbers or
Mhm.
multiplication of integers and multiplication of scalar products. I don't know. I'm pulling that one out of my butt.
But yeah, that's the idea behind all this, is that sometimes you're trying to prove something about a particular set and the binary operation that you're dealing with, and it's very, very hard. But for the isomorphic group, like the other group, it's a lot simpler to prove those same results. So what you do is you go to the other group, you prove those results, and you use the isomorphism and then say, therefore, it must hold for the other one as well.
Okay.
Yeah. So it's a
And
tool that you'll learn to use.
And because phi is bijective, we can go the opposite direction because
Exactly.
there must be an inverse phi.
Exactly. That's right. Mm-hmm.
Oh, neat. So we could technically go to as many different domains as we want, provided that there's a phi that connects them all.
Mm-hmm.
Oh, cool. I never have to add things ever again on the real number line. I'm just going to talk about other things instead.
Pretty much. Yeah, like one thing you learn when you start taking this class is that there's a lot of things that behave just like addition, and there's a lot of things that behave just like multiplication.
Oh.
Yeah.
That's great, but also terrifying.
But yeah, that's kind of where I'm kind of walking you through with this worksheet here. When you get to like towards the end of it, that's kind of you're foreshadowing it. So that's good.
Cool.
All right, I'll be right back.
Okay.
If goes with like the different elements, can it be same?
Can it be what now?
Yeah, because if it's the three different elements, it will be goes like ABC and ABC.
Uh,
I have no idea.
Are you guys talking about C or D?
D.
D. Yeah.
D. Okay. Do you get what the question's asking?
Not really.
So it's saying let's just pick a set with 3 random things. Like just create your own elements. What do you want them to be?
We'll just.
Let's say you pick numbers, okay?
Okay.
And we're gonna use the let's pick numbers, and I want you guys to pick, and they could be integers or fractions or whatever kind of number you want, but pick 3 of them so that they form a group with, and you can pick either with multiplication or with addition or whatever.
Okay.
Let's see if we can do that.
Let's just do, I guess, addition. Why not? We'll go.
Remember,
0.
it needs to have an identity, and it needs to have everything has to have an inverse as well.
1, -1.
So what's the inverse of -1? Oh, I guess 1, huh?
Inverse of -1 is 1.
Yeah.
And then 0 is the inverse of 0. 0 is our identity. So I think this is a group with addition.
Let's see.
Oh.
What would happen if you add 1 plus 1?
0.
Oh,
Not 2.
get 2, yeah.
Crap. Okay. What if you did multiplication? Oh no, because you can't do 0, huh?
If we did multiplication, we would have 1 as our identity.
Yeah. Maybe numbers might be too hard to make an example of a group.
Okay.
Oh, what if you guys did, let's say, Z mod 2? I think that has 3 elements, right? Number Z mod, integers modulo 2 with equivalence classes.
Yeah.
The equivalence class 0, the equivalence class 1, and, or I guess Z mod 3 then.
Z mod 3?
Yeah, what elements, do you guys remember what elements those are?
Class 1.
Equivalence class 0, everything with remainder 0 when you divide it by 3, everything with remainder 1,
Class 2.
and class 2. And I guess here, what binary operation do you want?
I'll just do multiplication, or that's fine.
Okay. Then what would be the identity here?
The equivalence class 1.
Okay. So then what would be the inverse of the equivalence class 0? Maybe try plus. Try
Plus,
addition.
okay. Plus, we'll do addition.
All right, so try that. Try addition and fill this table in.
Okay.
And then see what happens. I'll be right back. Let me go check on the other folks.
Okay.
How's it going?
We are thinking about why some of these are not, what's the word for it? We're thinking about why the table that we're doing here, whether or not it is a group or not, basically.
Okay.
So, okay, this is my specific example. Let's check if that's actually true. 1 with 1 is 1. Yeah. Wait, no, that's wrong. Whoops. That doesn't work. Those are equal. Wait a minute.
Yeah, because it says that there has to be only one element in every row and column for it to be a group. And
Yeah,
that,
so
I don't know, I guess I'm not convinced.
yeah, we're trying to figure out why that would be. Is it because it would break associativity?
This group or this table you guys made here?
Yeah, sure, like this table.
Okay. So you guys are trying to, one of you is, or both of you trying to check that it's not a group.
Yeah.
Okay, I got you. Oh, I see. Okay. What did you guys, can I see what you got for the table on tops, the ones on top?
Well, we don't have it saved anymore.
Oh,
But,
okay. That's fine.
Yeah.
Okay, here's what I'm thinking of. So anything with the identity in it is going to work because the identity will affect anything.
Mm-hmm.
So that means we have to come up with combinations that only use 2 and 3, which means there'd be 8 combinations. You know, because you have 2 possible options for 3 spots, so 2 to the third is 8.
I think I'm going to need a specific example.
Okay, so what I'm saying is 1, since it's the identity, it can always be removed. It's never going to affect, like if you do a 3-way thing for association,
Right.
it's going to cancel out no matter what. And
Right.
So you have to, if we want to test all of the things for associativity to see if it fails any of them, we should just go ahead and test ones that only have 2 and 3 in them.
Yeah. So that's okay.
Which would be
Switching.
8 different combinations. So if we test all 8 different combinations and they all work out, then we can say this is a group because 1 is the identity, everyone has the inverse.
So something like this would fail, depending on like which, if you apply what's the word for it? If you apply the, oh my God, words are so difficult. If you apply the row then the column, I think that's what I'm trying to say. then these two are not equal to each other.
Okay.
Because the top one is just 3 for sure. Whereas with the bottom one, you apply like 3 with 2, that's going to give you 3, and then 3 with 2 again, that gives you 3. So, no, wait, those are equal. Oh my God, no.
Wait, 2 times 2 is 1. So
If you apply column then row, then it breaks. There we go.
oh yeah, you're right. This does work.
And if you apply column and row, then it breaks. So like, okay, this is equal to 3 regardless of what you do, right? In this case. Mm-hmm.
Wait, are you doing row then column or column then row?
So I'm like, okay, 3 comma 2 would be like, I'm thinking for this specific, because you can just mirror it and it's going to break. Like if you wanted to do the other way, right? I'm thinking of 3 comma 2 being this one. That's probably the opposite of how we're supposed to do it, right? I keep on forgetting.
I think we just choose one direction and then.
Okay.
Can I ask you guys a question?
Mm.
So, what's your identity here? What's your identity element?
I actually didn't hear any of that, unfortunately.
Oh, sorry. Can you hear me now?
Yeah.
What's the identity element in this table that you're thinking is the identity element?
It's 1.
Yeah, you cut out a little bit, but it is 1, yeah.
Okay. So then, if you
he's still gone.
If you, oh dang it, can you hear me? Can you hear me now? Hello.
He froze.
Dang it. Okay.
Yeah,
Can you hear me now?
Yep.
I guess I want you guys to notice that there's a 2 here and there's a 2 here.
Yeah.
So with this 2 here, how are you guys like combining it? Like which number are you is that 2 star 1? Or is this 2 here 1 star 2? I'm just curious.
Oh, right. So the way that I'm thinking about it for my specific example to break, that 2 there would be 1 star 2. That's probably the opposite of how we're supposed to do it, right?
Okay, 1 star 2. So you're getting 1 star, that's my shitty star, 2 equals 2. But then you're also saying that 3 star 2 equals 2 as well, right?
Mm-hmm.
Yeah, but I don't see why that's necessarily a problem.
Well, what's your inverse of 2 then?
The inverse of 2 is 2.
Okay, so then if your table is saying that 1 star 2 equals 3 star 2, and then if you apply the inverse of 2 on the right of both sides of that equation, what would happen if you applied the inverse of 2 to both sides of the equation?
Oh, interesting.
So you get 1 star 2 inverse equals 2. Oh,
1 equals 3, yeah. Okay, very interesting.
Okay. Thanks for saying.
So be careful with that, yeah, because now you're saying there's 2 identities.
Right. And this also works, but yeah. I think that's a much clearer example. Okay.
Okay, I'll be back, guys. Good job. So is this a group?
This is not a group.
Okay.
So all groups of 3 elements must be isomorphic.
That's our conjecture.
Cool. All right. So there is one that you guys know, actually, like a real life one.
Mm.
It's I think it's this one here, Zmod 3 with addition.
Mm-hmm.
I believe that's an actual group with an actual binary operation that we've defined.
Oh yeah.
Right?
Mm-hmm.
So according to your conjecture, that is also isomorphic to everything you've been doing so far.
Yes.
Cool. Okay. All right. I'll be right back. Let me just check on one more group.
Sorry.
How's it going? So what'd you guys get? Let's see.
Just pretend these are all equivalence classes.
Totally, yeah. So is this group different, meaning not isomorphic to the ones on top?
I'm pretty sure it's still isomorphic, unless we really need this operator to be composition. But I'm pretty sure it is.
Mm-hmm. Yeah, I mean, if it was, what would be the bijection here, or the isomorphism? I think it would be. Oh, yeah, I see it right there. Okay.
Yeah.
Okay. Okay. So what do you guys think? Any conjectures?
Perhaps every group table with 3 elements is going to be isomorphic to this group G comma star.
Mm-hmm. Yeah, and since this group that's isomorphic, this group G, you just shown as isomorphic to this group Z mod 3. You can change your conjecture to saying that they're all isomorphic to Z mod 3 as well.
Okay.
With addition, that is.
Mm-hmm.
Huh, interesting. Okay. All right, cool. Let's go back to the weight room here. Take a quick break. Let me just tell everybody. Okay, let's see, what time is it? Do you guys have it on there? Oh, here it is.
5:07.
5:07. Okay. Let's take a quick break and resume at, let's see, 5:07, 17, 5:17. All right. I'm going to close the group in a little bit, okay?
All right.
Yep.
Just going to check out what you guys have on here. Cool. So I'm going to close the group.
Yep.
All right.
Cool.
Yeah. So the multiplication of integers mod 3 are definitely not going to be a group because it's going to fail associativity.
Mm. So okay, if we did this right, then we should be able to basically like somehow turn the left table into, you know, everything that we've done so far, right?
Yeah, it would all just. I think it's already in that order. You would just have to do 0 goes to A, 1 goes to B, 2 goes to C. The table that we erased.
Maybe, yeah.
You know, because you have 0 is the identity,
Mm-hmm.
and then you have 0 is its own inverse, and then you have 1 and 2 are each other's inverses. I honestly should just be typing because this is. Oh, so then you have 1 equals 2 inverse, and 2 equals 1 inverse. So yeah, if you had phi from the integers modulo 3 to our other group G, then you would have phi of 0 equals our identity A, and then the other two don't matter as long as they go to distinct. You know, because you could have phi of 1 equals C or phi of 1 equals B. It wouldn't affect it.
Okay.
The only thing that matters is that it preserves the identity.
Right.
But these two are going to be functionally the same.
Interesting.
All right, we solved it.
That's good. So whatever. Okay, I can keep adding. All right, take a break. Take a break. Come back at 5:15, 5:17.
Okay.
All right, I'm gonna close the rooms. Okay.
Okay.
Mhm.
All right. Let's see. Okay, let me just put that in the chat again. Okay, pause. The Zoom class. Make sure you're back. I wish there was like a little ding, ding, ding to put up there. Okay. So just on the chat, make sure you say I'm back or just back, just so I know. Cool. All right, let me start projecting my iPad. Using my share, make sure I'm recording. Am I recording? Yeah, okay. All right, great. So it looks like everybody's conjecture was that any group or any set with 3 elements and a binary operation, if it forms a group, then it's going to have to be isomorphic to this group G here. And then I had you guys play around. Some of you guys were playing around with Z mod 3, which had the equivalence classes 0, 1, and 2. And you were using the binary operation of addition. And since this is a set with 3 elements and addition makes it a group, then your conjecture can be rewritten so that any group of 3 elements is going to be isomorphic to Z mod 3 with addition. And then I was talking to another group how your conjecture is that here you have some binary operation if G equals, the cardinality of G equals 3, right? That's kind of like your conjecture here. I'm being very informal. So I was discussing with another group the benefit of this isomorphism is that am I muted? Let me see here, the chat here.
No, you're good.
Okay. The cool thing that about this isomorphism, or of isomorphisms, is that your groups here can be very abstract and your binary operations can be very different, but because they're isomorphic to a quote unquote nice group where it's just addition and the elements are not that nasty, that since they're isomorphic, that means that any group that you're dealing with that has 3 elements is pretty much behaving like you're adding the numbers 1, or the equivalence classes 1, 2, and 3. So that means that if we had A, B, C here, A, B, C, and let's say your isomorphism maps, let's see, 1 to B, and sorry, the equivalence classes to C, notice that when you add the equivalence class 2 with itself, what happens when you add the equivalence class 2? What's 2 plus 2? That's gonna 2 plus 2.
1.
2 plus 2 will give you the equivalence class 4, which is equal to the equivalence class 1. So like basically the cool thing about this is that whatever properties you find in this group carry on to this group. So for example, the equivalence class 2 plus 2 is equal to the equivalence class 1. So what happens if we add the equivalence class 2 with itself 3 times? What do we get here? We're going to get 6. But when you divide that by 3, that has remainder 0. So notice that that's equal to the equivalence class 0. So when you add this equivalence class with itself twice, you're getting this equivalence class 1. But when you're adding it with itself 3 times, you get the identity. Since this holds true within this group, that means that it must hold true within this group G. That means that if I combined A and I start it with itself, oh shit, not A, let me use, we were using C here. If you did C star with C, according to what behavior is happening in Z mod 3, it must also happen in this group G. That means it should be equal to the element in G corresponding to the equivalence class 1. So this should give me B. And if you guys filled in the table here, A, B, C, I think this was what? A and, oh no, C and A, and this was A and B. Let's see, C star C, that gives me the equivalence, the element B, so that holds. And if I combine C with itself 3 times, because the equivalence class added with itself 3 times gives me the identity, that means that if I multiplied C with itself 3 times, I better get the identity as well, which is in this case going to be A. So that's a little harder to check with the table, but this is exactly the whole point of isomorphisms, that whatever larger, more complex properties happen in this group, they follow through to the other group. And that's kind of the benefit of isomorphisms, that sometimes you have 2 groups that are isomorphic, but one of them is a little bit easier to play with and prove things with than the other group. It might be very like too much detail or too much notation, and it's very frustrating. So what mathematicians do is they find a group that it's isomorphic to, and if the objects are simpler, you prove what you were originally trying to prove here. You prove it in this group, and then the isomorphism will then force it to also be true within this group. So that's kind of the benefit of isomorphism. Cool, right? I think that's super cool. So let's see. So some of the properties that you were noticing in the group problems right now are the following theorem. So if you have two groups, so G and H, let those two groups be isomorphic, or let them be isomorphic groups with identities E and G and T and H, respectively. If phi is an isomorphism between them, then when you plug in the identity of G into the function phi, it has to map it to the identity in H. And if you plug in the inverse of G into phi, it's going to map it to the inverse of the output of G. Okay? So that's what's called preserving identities and preserving inverses. Okay? So I want us to now actually like keep working on proof techniques here. So I want us to only do one. Let's see how much time we have. Yeah, I think we only have time to do one. You guys pick. I didn't make a poll for this. So just on the chat here, there's only a small number of you, so it'll be fine. Do you guys want to prove 1 or 2? Property 1 or 2? We'll do it as a class, step by step. 2 inverses. All right. That one seems a little more complex. Okay. So let's see here. So we're going to pick 2. So we want to show, let's pick 2. Let me just define everything then. So let G star and H with a dot be isomorphic, and let phi between G and H be an I spelled that wrong, isomorphism. Okay, so I'm starting my proof. Don't forget that you don't just jump into proving the property you're trying to prove. You always have to tell the reader the symbols and the functions. You have to kind of spell it out for them. What are the objects that you're going to be using? Okay. So let's see. Now we have all our assumptions here, or sorry, all our definitions. So if phi is an isomorphism, so we're going to say it is, then we need to show that we need to show this, and this is a little abstract, okay? And let's see what that means.
Excuse me?
Yes.
Will we be assuming property 1 for our proof in property 2?
Say that again?
To prove property 2, will we be assuming that property 1 is already true?
Let me see. You don't need that. No, you don't need to.
Okay, thanks.
Yeah. Mm-hmm. But what you do need, oh, we didn't write these things out. We forgot to write the identities. Okay, so let me restart, because we do need to know that there are identities. Which are the identities? But property 1 won't be necessary to prove property 2. Well, or let's go for it. Let's jump into it and see if it is. Be isomorphic groups. I didn't say that. Whoops. Such that E and G and T and H are their identities. So let's see. Okay, let me make sure we got everything. Okay, so G isomorphic. These are the identities. So technically, if we ignored statement 1, this is an if-then statement. If this function is an isomorphism, then it should preserve inverses. So since it's an if-then statement, let's just define a function and suppose that it's an isomorphism. So define the function phi from G to H, and suppose phi is an isomorphism. Okay. So I think we have everything. We have our identities, our groups, and our function here that we're supposing is an isomorphism. And then let me just remind you the two things that come along with an isomorphism. Okay, it's not just the order preserving part. These are the two things that follow through by it being an isomorphism. One, we can assume now that it's a bijective function. And we can assume that it's operation preserving. Okay, so those are the things that we can use: bijections and order preservingness. That is what we get now by assuming that it's an isomorphism. Okay, so let's see. Let me just so we can visually see it. Let me just copy here. Okay. So we need to show. That. Okay. That's kind of where we're headed now. So we haven't proved anything yet. We are just kind of laying out all the foundational notation and our assumption that we have an isomorphism. So this part here is what I want to talk about. Okay. First, we need to show that this is true for all G in our group G. So let's start by picking an arbitrary element in G. So let's start with that. We're going to say let G be in G. Okay. Let me explain what this notation means here. If G is in G, then where does phi of G live in? What is that an element of? Where does that output live?
H.
It lives in H. Good. It lives in H. And because phi of G is now an element of H, and H is a group, what should this element have?
It should have an inverse.
It should have an inverse. Okay. So let G be in G, then phi of G is in H. Since H is a group, phi of G has an inverse, phi of G inverse, but it's like on the outside. Okay, so it's kind of like, it's like that. It's the inverse element. But I don't want to write it like that. I'm going to write it like this. Is that cool so far? It has an inverse. Okay. All right. A little quick check-in. How's it going so far? Okay. So let me just reiterate for proof in terms of proof technique, because I feel like I haven't been kind of stressing that in a bit. The proof right now, this is just the definitions. Here I defined a function, and I'm supposing that phi is an isomorphism. Remember that we're trying to prove that if phi from G to H is an isomorphism, then property 2 holds. So remember that this is an implication. It's an if and then statement. So right now we're applying the direct proof technique. Don't forget the techniques. So always have a plan of attack. Not now, it's not just for like what the objects are, but it's also, don't forget what are the techniques that I was, that you're going to use, because that was the important thing I told you guys when we were going over proof techniques, is first decide on the technique, because there might be different techniques, and then which one do you think might be what might get you to what you're trying to get to in a less complicated way. Okay, so we don't even want to start using contrapositives here, because that sounds nasty. A direct proof seems to be the fastest way. So I assume this is an isomorphism, and now I need to show that this statement here is going to be true for all G and G. But because these are new math objects, you first need to also say, what the hell is this? I think this you get, but this probably was a little weird. Okay. So we're writing, I'm now in my proof, we're writing what it is because of where the element phi of G lives. But now what we need to show is that this element, the inverse, is really just equal to what you would get if you plug in the inverse of G into phi. Okay, so I want you guys to notice the difference. G is in G, capital G, the group, and then you plug that into phi, it's going to send it to some element H. The inverse of that element is denoted this way. But now the claim is, well, what I could have done instead is, for this little g, is because that's in a group, it itself has an inverse. And instead, I could have just plugged that inverse into phi. And then this h that I'm going to get is going to be equal to this h that I'm going to get. Okay? So that's what we need to show. But the question is, how do we show that this is indeed the inverse of phi of G? That's the part that's hard. Okay? So how are we going to show that when I plug in the inverse of G and then plug that into the function, that will indeed give me the inverse of phi of G? So here, this is not part of the proof, but I'm just going to put it to remind you guys here. So I'm going to put it in blue. Recall that if that when you have an inverse, that for H and H, when you combine them with its inverse from both sides, what do they need to equal?
The identity?
Which is what in this example?
T.
T. Okay. Because phi of G is an element in H, that means that when you multiply it or combine it from either side, okay, with phi of G, we need to always get T. That needs to happen. That's just what it means to be the inverse of it. That has to have that property, okay? So in this case, we already know that this right here and if I do it on the other side, is going to give me T, because this is just a symbol that means the inverse of phi of G. So we already know that that's supposed to be true, because that's by definition what it means to be the inverse. So now what we need to show that this is the inverse, we need to show that it also does the same thing if we multiply it on both sides from the left or to the right, that we're going to get T. If we can show that when we multiply this to phi of G on both sides and we get T, bam, that tells me that this element has to equal the inverse of phi of G. Okay? So let's see. let's do that. So since G is in G and G is a group, G inverse exists. G inverse in G exists. It has an inverse. And because it's in G, we can plug it into our function. So therefore, let's see what happens if we do this. So I'm going to multiply phi of G inverse, phi of G with phi of G inverse inside. Okay? So I'm trying to mimic this behavior here. But notice that this is the inverse is outside, while here I'm saying this is the inverse of G. Okay. Notice also that I'm using the binary operation of H because these are now both elements of H. Okay. All right. So what should this equal? Given that phi is an isomorphism.
It should equal T, right?
Well, that's what we're getting to, but we can't jump. We can't jump straight there because we don't know if this is the inverse. Yeah, we don't know if this is the inverse. Okay.
Would it be phi of G star G inverse?
That's right. Now we're going to use the fact that phi is order preserving and say instead of multiplying outside, I can use the binary. I keep saying multiplying. Instead of combining the elements from the outside, let's combine them from the inside. And so now I can have phi of G, but now I have to use the binary operation for G, which, what's the symbol we used? Star G inverse. Oh, we do need it. All right, Avery, so we do need property 1. So we do need property 1, okay? Now G star G inverse, these are inverses of themselves. So they'll give you phi, they'll give you the identity. And then from property 1, and here's where Avery was saying it was going to be needed. Phi maps the identity of G to the identity of H. So then we get T here. And then similarly, we can do the same thing on both in the other direction. Because it's an isomorphism, I can do it from the inside. But because it's the inverse, it doesn't matter which order I multiply it with. That gives me the identity, which is going to be T. So hence, we can multiply this element on the right or combine it from the left with phi of G, and I get T. And because it has this property, that means that when I plug in the inverse of G into phi, it needs to output the inverse of phi of G. So so therefore, hence blah blah blah, thus phi of G is the inverse of phi of G, which is equivalent to saying that phi of G inverse equals phi of the inverse of phi of G. Ugh. And so that would end the proof right there. Okay. So let me give you guys a little visual here. So let's say here's the set G, and here's the set H. Okay. Here's the identity. Here's the identity. Phi has to map the identity to the identity. And here's G. Let me write it over here. Let me zoom in a little bit. Here's G. And when I plug G into phi, I'm going to get some element H. Okay. And then H has its own inverse. There can be a different element in my set G that maps to my inverse, right? There could be some other random element. But what we just proved is that it isn't some random element. The only one that maps to the inverse of H has to be the inverse of G. That's the only one that is able to map to the inverse of H. It's the inverse of G. Does that visual kind of help? Kind of? Let's see here. Let me just get a quick check. This is the first time we're seeing like a proof with this stuff, so it's pretty weird, but visually that's what's going on. Okay, now visually I think understanding it might be okay, but this part here, guys, this is the part that's going to be a little hard. Making these arguments, you really kind of have to dive deep into what's going on. Okay, especially this notation. For me, when I was a student, I was very confused by it. These two to me meant the same thing, but they mean different things. Phi of G inverse means I mapped phi of G, I got an H, and then I'm looking at the inverse of it, which is H inverse. While this one means I'm looking at G inverse, I plug it into phi, and I'm going to get that same H inverse. Okay. Let me make sure. I think we're last time am I still recording? Okay, good. All right, so let's see. So this is just a proof to show. It's not proving anything about two groups being isomorphic. It's proving a property about an isomorphisms between two groups. In these problems, you guys were able to show that these two groups were isomorphic because they only had 3 elements. And you saw that it was order preserving, because when you multiplied B with C, for example, from the table, you were able to clearly see that it was the same result or similar behavior as if you multiplied Y with Z. Okay. So in this case, there's several ways you can prove isomorphism. If your sets are finite, then you can just go ahead and make a group table. And then once you make a group table, you can see, oh yeah, I see that they're isomorphic because they're behaving the same, and therefore I'll just send A to X, B to Y, and C to Z. And that's your function. That's your function, so that's going to be your isomorphism. And it's order preserving because you'll clearly see it on the table. But what if the set is an infinite set and you don't have time to make an infinite table? How are you going to prove all this stuff abstractly? So I want to show you guys here an example. So here we have 2 groups, the integers with addition and the even numbers with addition. Both have the identity 0, and they both have inverses. So we need to prove that these 2 groups are isomorphic. Again, notice that when they use this notation, they don't use the binary operations. You kind of have to understand which binary operations they're talking about when they do this. Okay. So because we need to prove they're isomorphic, we need to prove that there exists an isomorphism. Okay. So let me actually let me write that in red. So the proof here is an existence proof. We need to prove existence of an isomorphism. So the overall structure of the proof will be an existence proof, but because we have to show it's an isomorphism, we have to show that it's a bijection, that there exists a function that's a bijection in order preserving. So within each of those steps, we're going to then also use their own different proof techniques. So this is kind of a proof that uses different types of techniques. So the overall one, though, will be isomorphism. So then you tell yourself, okay, I need to show it's a bijection. To show something's a bijection, you need to show it's injective and surjective. So let's see here. So I'm starting by just telling my reader what I'm dealing with. So consider groups Z with addition and the even numbers with addition. And define phi from Z to 2Z by plugging in an integer and then doubling it. We already showed earlier this was a bijection, but let's just do it again. So here I'm just defining my function. Now we're going to go into the proof technique and show its injection. So I need to show an if-then statement. So let n1 and n2 be in Z and assume that phi of n1 equals phi of n2. So that is equivalent to just saying I'm going to double each of those. And then if I divide by 2, that's equivalent to saying n1 equals n2. So I was able to show this implication here. It's in this case, it's an equivalence. But we can show that the implication is true, therefore it's injective. Okay, so you told the reader it's injective. I can add a little bit more wording here if I want, but I'm just going to give it the main skeleton of what I need. So I could tell the reader, okay, now to show the phi is bijective, we just need to show that it's surjective, but I didn't want to write that just to save time. So we're going to jump into it. So now we need to show it's surjective. So therefore, we need to show that for every element in the codomain, there exists an element in the domain that maps to it. So let M be in the codomain. Because those are the even numbers, that means there exists an integer such that M equals 2k. So period, stop. Okay, that's just the definitions. Now we're going to say, hey, since k is an integer, when I plug it in, that means it lives in my domain. When I plug it in phi, look what happens. So I plug in k, I get 2k, but that is just exactly what M is. So it has an input, k. So hence phi is onto. Let me just quick little check-in. You guys are probably going to get annoyed by these, but I can't look at you, so this is the best I have. How is it so far? Okay. So we showed it's a bijection. So therefore, since it's injective and it's onto or surjective, phi is a bijection. Check. We're done with that one. And then I can add a little bit more detail here if I wanted, and I can say, all right, so now we must show that phi is order preserving, but I'm just going to jump straight into it. So now consider n1 and n2 being integers. Then if I add those two integers and I plug them into phi, let's see what happens. So if I add these two integers and I plug them into phi, the sum of two integers is again an integer, and phi doubles integers. So I'm going to double the sum. Okay? And then I used phi. At that step, we used what phi does. Now we're not using phi. Now we're just doing properties of integers. I distribute the 2 in here. Nice. But notice that when you distribute the 2, this is the double of n1, and this is the double of n2. By definition of phi, I can rewrite 2n1 as me plugging in n1 into phi, and I can write 2 of n2, 2 times n2, as me plugging in n2 into phi. That part is really important, okay? So notice that we can go from here to here, since phi of n1 equals 2n1 and phi of n2 equals 2n2. And because I'm adding these two things, I can then say that it's like I'm adding the outputs of these elements. Since both groups use the addition, are using the addition binary operation. So I've just shown that if I can add them in the inside, plug them into phi, or I can first plug them into phi and then add them. And that's exactly what order preserving means. So therefore, phi is an isomorphism. So therefore, Z is isomorphic to even integers. They behave the same with addition. So that's the kind of stuff you'll be doing on the homework when you want to prove isomorphisms, okay? Is bijections and then showing order preserving, like that. Any questions on this step? That's the new stuff. Good? Okay. So let's see, we have only 4 minutes, so we don't have time to do these. That's okay. I was gonna, in case we had time, I was just gonna prepare you guys to start working on your homework problems. So here's the first homework problem that you're gonna have to do. It says, in each of the following, determine whether the function phi is an isomorphism from the first group to the second group. We kind of just did part A. So if you map phi from the same group to itself, but using this function. Now let's look at like the third one, for example. R with addition to the group of positive real numbers with multiplication. Is this an isomorphism? Okay. If it is an isomorphism, then that means that you adding real numbers is practically the same kind of behavior as multiplying positive real numbers. Who knows? Okay. Let's see here. So, and then there's other ones here. Are any of the following isomorphic? So now that I realized my notes were incorrect in the beginning, this is just a bonus. This is a group with 6 elements, a group with 6 elements, and a group with 6 elements. Are any of these isomorphic to one another? They only have 6 elements, so maybe you guys could draw some tables if you want, some group tables, and compare them and see if it's true. Okay? But that's it. This is the end of the abstract algebra chapter of this class. This is now we're gonna, in the next class, we're gonna jump into the real analysis part of it, and they're gonna feel totally different. So if this was like very weirdly abstract, the other one is a little bit abstract, but it's more detailed in terms of like, there's just a lot of details to it, which will, I guess they both have details, but it'll just feel very different. So usually in upper division math, you'll either branch into algebra, which is what this stuff is about, or you'll branch more into the real analysis stuff, which is what we're gonna do in the next 3 sections, or in the next 3 classes. So that's pretty much all we have for today. Let me just have you guys answer one more poll class for me, please. So I know if I should stay or if you need me to help you with something. No? Okay. Remember that this is section 13.6. So if there's something, okay, I got it. So if there's something that you want to look at some examples, I mean, as every math teacher tells you, look at the examples that they do in the book, because they do a lot of different isomorphism proofs. You might want to, I think they show some examples here, which we didn't have time, on how to show